Okay, everybody, so we're going to be talking about section 6.4, additional properties of linear transformations. Okay, so we need a new definition. So let T1 be a linear map or a linear transformation that goes from U to V, and T2 go from V to W. So suppose these are two linear transformations. We can define their composition. So we can define their composition as follows. So T2, T1 is how you compose the maps, and this is how you write it down. You write T2, T1, and now this is a map that goes from U to W. And the way it's defined by T2, T1 of U is equal to T2 of T1 of U. This is how we define the composition of the two maps. And so if we want to draw a visual of this, let's suppose that we have, well, let me actually do this on the next page. So let's say we've got U right here, and we've got W right here, and we've got V right here. So let's start with vector U. So T1 takes it right here. And so you can look at T1 as being the map that takes U to T1 of U, right? And now T2 maybe we'll take it right here. So this would be T2 of T1 of U. So let me write it this way. So this is T2. But now what we're saying is we can create a new map. Let me give this a new color. And this new map just goes straight from here to here. And this new map is called T2, T1. Okay? So this is what it does to every guy in U. We've just created a map that goes from U to W by just taking a map that goes from U to V and a map that goes from V to W and composing them, putting them together. Okay? So this is the same as T2, T1 of U. Okay, so you can look at it as a single new map of compositions, or you can look at it as a map and then another map applying to it directly after. Okay, so we have a nice result. So theorem. If T1 going from U to V and T2 going from V to W are linear transformations, then T2, T1, which goes from U to W, is a linear transformation also. Okay, so when you compose two linear transformations, the result is a linear transformation. How would we prove this? Well, we need to show that T2, T1 meets both axioms of being a linear transformation. So let's look at axiom 1. We need to see if the map distributes over addition. So let's actually start by saying let U1 be in U, and U2 also be in U, and then let's take a scalar, right? A real number. So T2, T1 of U1 plus U2 is equal to, remember, this is the same as T2 of T1 of U1 plus U2. But because T1 is a linear transformation, this is actually the same as T1 of U1 plus T1 of U2. But now, because T2 is a linear transformation, this is the same as T2 of T1 of U1 plus T2 of T1 of U1. But finally, the very last step is to recognize that these are just the composition maps. So what did we just show? We just showed that T2, T1 satisfies the first axiom of being a linear transformation. Okay? Let's prove the second axiom really quick. What's T2, T1 of CU1? Well, this is the same as T2 of T1 of CU1. But we know by the fact that T1 is a linear transformation, we know that this scalar can pull out of the first linear conformation. But now, because T2 is a linear transformation, C can pull out of the second linear transformation. But this is the same as C times T2, T1 of U1. In other words, we're done. This shows that T2, T1 is a linear transformation. Okay? So that is our proof. Now, let's move on a little bit, and this is a note here. Let me just write a note. Just because T2, T1 is defined, it doesn't mean T1, T2 is. Okay? And more importantly, in general, even if they both exist, T2, T1 is not the same as T1, T2 in general. Okay, this is extremely important. When you compose maps in a different order, just like you learned in algebra, you do not get the same function. Okay. So let's do a quick example here. So suppose, or let me just say if T1, which goes from Rn to Rm, has matrix A, and T2 from Rm to Rp has matrix B, can you compose T2 with T1? What do you think? Well, T1 says Rn to Rm, and then T2 takes Rm to something. So yes, T2, T1 exists, right? In fact, T2, and let me just write it this way, T2, T1 goes from Rn to Rp. So this does exist, right? Because the vector spaces, the targets and the ranges, the domains, all that stuff is correct. And what is T2, T1 of a vector x? Well, we know this is just T2 of T1 of x. So what's T1? Well, it says T1 has matrix. Let me get back to my colors here. T1 has matrix A, so I know that this is going to equal T2 of AX. But then T2 has matrix B, so this is going to equal B times AX, which is the same as BA times X by associativity of multiplication of matrices. So what did we just learn? This implies that T2, T1 has matrix BA. So this is nice. If we want to find the matrix of the composition of transformations, we just multiply the former matrices together. And by the way, let's check the numbers here. If T1 grows from Rn to Rm, then that means A is an m by n matrix. So this is m by n. And if T2 is going from Rm to Rp, then that means that B is a p by m matrix. And so when you multiply B times A together, this guy is, look at the dimensions, right? It would be a p by n matrix, which makes sense, right? Because it's going from Rn to Rp. Okay, so this makes sense. Let's try another example. Let's let T1, which is going from MNR to MNR, and T2, which goes from MNR to R, given by the following. So we've got two maps. I need to tell you guys what they both do. So T1 of a matrix is just the matrix plus its transpose. This is well defined, right? Because the transpose of an n by n matrix is still an n by n, so we can add these together. And T2 of A is just equal to the trace of A. Trace of A. So what would T2, T1 of A be? So T2, T1, well, let's look at their targets and their, let's look at the targets here. T2, T1 goes from, let's see, it goes from MNR to R. And let's see what T2, T1 of A is equal to. So if we compose the two matrices together, it means first we hit it with T1, and then we hit it with T2. When you hit it with T1, you get A plus its transpose, so you get A plus its transpose. And then hit it with T2, which is just to take the trace, you get the trace of A plus A transpose. But by properties of trace, we can actually write this a little bit nicer. We get this. However, the trace of a transpose is the same as the trace of the original matrix, right? Because the diagonals stay the same, don't they? So this is actually the same as 2 times the trace of A. So what we have found is that T2, T1 of A is equal to 2 times the trace of A. Okay, so let's move on to a new definition. So we're going to define what it means for linear transformations to be one-to-one and onto. So a linear transformation T, which goes from V to W, is said to be, first, let's define one-to-one. So it's said to be one-to-one if distinct elements in V are mapped via T to distinct elements in W. Okay, so different things in V go to different things in W. So how would you write that with symbols? So it looks like this. For all V1, V2 in V, if V1 does not equal V2, then T of V1 does not equal T of V2. Okay. So this is what it means to be one-to-one. And let me give you the definition of what it means for a map to be onto. That's ONTO. It's one word. Okay? So a transformation is onto if the range of T is equal to W. Okay, this is important. This means the range is the entire set W. So i.e., what another way of writing this is, for all W in W, there exists a V in V such that T of V is equal to W. Okay, so this is a symbolic way of writing that a map is onto. Okay. So let's do an example here. Let's write down a map and figure out whether it's one-to-one and whether it's onto. Okay. So let T, which goes from M to R, be defined by T takes a matrix to its trace. First, is T 1-to-1. And second question, is T onto? So let's think first, is T a 1-to-1 map? Do distinct matrices always go to a distinct place here? Well, is it true that if two matrices are different, then they have different traces? Well, that's definitely not true, right? What about T of 1, 2, 3, 4? That's equal to 1 plus 4, which is 5. And how about T of, oh, I don't know, how about 1, 0, 0, 4? Doesn't this have the same trace? In other words, we had two different matrices go to the same place. So the answer is not 1-to-1. Now, is T onto? Well, is it possible to get every single real number using a matrix to get its trace? The answer is yes. Okay, look, take any real number you want. Let's call it C. What would be T of the matrix C, 0, 0, 0? It's equal to C. In other words, it's possible to get any answer you want just by creating a matrix like this. So yes, T is onto. Of course, that matrix I picked was not unique, and that's the whole point. There are lots of things that map to each one, so we know that we can get the whole real number space by just putting any matrix we want in there that has the correct trace. So there's an example of a map that's 1-to-1, or sorry, that's not 1-to-1, but it is onto. Okay. All right, so we now need another theorem. So let's let T, which goes from V to W, be a linear transformation. This is one of the most important ways of checking that T is 1-to-1. T is 1-to-1 if and only if the kernel of T is equal to the trivial subspace. Okay, T is 1-to-1 if and only if the kernel of T is the trivial subspace. So what does if and only if mean? If and only if means that it's a double-sided arrow. In other words, if you want to prove that something is true if and only if something else is true, that means that you have to go both directions. Okay, so let's start with T is 1-to-1. So let's do a proof. So the proof, we're going to start with this direction, okay? So that means we're allowed to assume that T is 1-to-1. We want to show that the kernel of T is the 0 vector. Okay, so we want to show that the only thing in there, inside of the kernel, would be the 0 vector. Okay, so how do we do that? Well, T of 0 is equal to 0. Okay, we already know this. This is something that we proved earlier about linear transformations. They always take 0 to 0. Thus, since T is 1-to-1, Remember, what it means to be one-to-one is that different elements have to go to different places. So this means that no other vector in V can get mapped to 0. So what this means is that the kernel of T is equal to 0. Remember, the definition of kernel is all the guys that get mapped to 0, and so the only guy that can get mapped to 0 is 0 when it's one-to-one. Okay, so now let's prove the other direction. So we want to suppose now that the kernel, and this is the more useful direction, let's suppose that the kernel is 0. We want to show that it's one-to-one. How do we show that it's one-to-one? We have to show that if you have two different guys, then there is no way we want to show that if we have two different guys, that they have to go to two different places. Okay, so let's let V1 not equal to V2 in V. So let's take two guys in V and let's suppose they're not equal. Then this implies that V1 minus V2 is not 0. What does this mean? Well, if we apply T to V1 minus V2, then what does that mean? Well, since it's not 0 and the kernel is 0, this must mean that this is not 0. So let me make sure you guys understand this fact. Because the kernel is the 0 vector, this means that only the 0 vector gets mapped to 0. So since V1 minus V2 is not the 0 vector, that means T of it does not go to 0. But this is the same as T of V1 minus T of V2 not being 0. And what did I use here? I used axiom 1 of linear transformations. But if I add T of V2 to both sides, this means that T of V1 is not equal to T of V2. So what did I just show? I showed that two different guys get mapped to two different places. In other words, this means that T is one-to-one. That's the definition. Okay, and that's the proof. Okay, so this gives us a nice, easy way to figure out if a map is one-to-one. All we need to do is find its kernel and see if it's just the 0 vector. Okay, so let's do an example. So let's suppose that T, which goes from R7 to R5, is a linear transformation, and the dimension of the kernel is equal to 2. Two questions. First, is T one-to-one? And second, let me back up here. Well, actually, I'll ask them both together. Is T on 2? Now, what's nice about this is we can actually use the rank nullity theorem to answer this question. So recall the rank nullity theorem. The rank nullity theorem says that the dimension of the kernel of T plus the dimension of the range of T is equal to the dimension of V. So what are all of these things? Well, the dimension of V, we know that this is 7, right? Because this guy right here is our V. Okay, so we know that's 7. We also know the dimension of the kernel because the problem tells us that this is 2. This means that we can figure out what this is. This must be 5, right? Because 2 plus that number has to equal 7. So let's go ahead and answer both questions. Let's start with, sorry about that. Let's start with the one-to-one part. Since the dimension of the kernel is 2, which is not 0, the theorem says that T is not one-to-one. Okay, so again, let's go back, right? The theorem says that the kernel of T has to be the 0 vector. That is the same statement, guys, as the dimension of the kernel of T being 0, okay? Because the only vector space that has dimension 0 is the trivial subspace. Okay, so let's go back. We know that T is not one-to-one, so that's the answer to part 1. And what about part 2? Well, we could tell a lot from dimension, especially when they're nice numbers like this. Dimension of the range is 5. And recall that the range of T is a subspace of R5. So what does that tell us? Well, if you're a 5-dimensional subspace of R5, you must be the whole thing. So this implies that the range of T is equal to all of R5. Remember, guys, that is the space we're mapping into. In other words, our range is the whole space, so this means that it is one-to-one. So this implies that T is, sorry, not one-to-one, onto. This implies that T is onto. Okay. All right. Let's go ahead and try another example here. So let's let T, which goes from, this time we're going to go from R3 to R6, be a linear transformation. And suppose the range of T is 3-dimensional. One, is T one-to-one? And 2, is T onto? So again, I want us to look at rank nullity theorem. So let's look at rank nullity theorem. Rank nullity theorem implies that the dimension of the kernel of T plus the dimension of the range of T is equal to the dimension of V. Well, V, remember V is R3, so this is 3. And it says, suppose the range of T is 3-dimensional. In other words, this guy would be 3. So then what would the dimension of the kernel be forced to be? Well, the only number that if you add to 3, you get 3 would have to be 0. Okay? So let's go ahead and answer the questions then. So first question, the dimension of the kernel is 0, which implies that the kernel is the trivial subspace. This implies that T is 1 to 1. Okay, so that is the first part. Let's look at the second part. Is T onto? Well, the dimension of the range of T is equal to 3, and the range of T is a subspace of R6. So what can we conclude from this? Well, if the range is 3-dimensional, it can't be all of R6 because R6 is 6-dimensional. So this implies that the range of T is not equal to R6, which implies that T is not onto. So rank nullity theorem is extremely powerful, especially when we use it in combination with the theorem about being 1-to-1. Let's do one more example. This one will be interesting, a little bit trickier. So here, let me write this down. Let's let T, this time we're doing a map which goes from P2R to P2R, be defined by, I have to tell you what to do with a polynomial. So we're going from P2R, so let's suppose that we're going from this polynomial, and when you take this polynomial through this map, you end up with the following polynomial: 2a minus b plus c plus b minus 2a times x plus cx squared. So we're going to answer the same question first. Is T 1-to-1? And then second, is T onto? Okay, so let's begin with the first question. Is T 1-to-1? We need to figure out what the kernel of this map is. So the kernel of T is equal to the set of all polynomials such that the map sends it to 0. So in other words, we need all 3 of these pieces to equal 0. So this means that 2a minus b plus c is equal to 0. Negative 2a plus b is equal to 0. And c is equal to 0. Okay, so it's the set of all polynomials that satisfy this. Okay, so I want us to go ahead and write this. This guy right here we can figure out by just solving a system. Okay, so when you do the augmented matrix for this system, we get the following matrix. We get 2, negative 1, 1, 0, negative 2, 1, 0, 0, and 0, 0, 1, 0. So we are going to add row 1 to row 2. So we're going to do 1 times row 1 added to row 2. And we're also going to multiply row 1 by 1/2. So row 1 by, let me write this correctly here. Multiply row 1 by 1/2. We end up with the following. 1, negative 1/2, 1/2, 0. Adding these two together, we get 0, 0, 1, 0, and then we also have 0, 0, 1, 0. Something bad is about to happen, right? We're going to add negative 1, row 2's added to row 3, and we actually eliminate the third row altogether. What does this mean? We actually have infinitely many A's, B's, and C's that work, right? So this implies, well, let's go ahead and actually solve this thing. So I see a free variable here. Let's say that y is equal to t. This means that z is equal, or sorry, these are a, b, and c. So let me back up here. B, that's right, it was a, b, and c. So b is equal to any real number, c is equal to 0, and then we have a is equal to 1/2 times t minus 0, which is 1/2 t. Okay, what does this mean? This means that because we have one free variable, or let me just go ahead and tell you what the kernel is, and we don't actually need to speculate here. The kernel of t is going to equal all polynomials that look like this. 1/2 t, t, and 0. Okay? Which is the same as the span. Oh, sorry. This is a polynomial, so let me write it as such. Plus tx. And then c is 0, so let me just write it that way. But this is the same as the span of the polynomial 1/2 plus x. Okay, so what did we just conclude? The kernel is definitely not equal to just the 0 vector polynomial, right? And so what we just determined, this implies that t is not 1-to-1. Okay, so let's go ahead and write down the dimension of the kernel, because we're going to use it for part 2. The dimension of the kernel, if we come back, we've actually only got one guy in here, right? And so this is a one-dimensional subspace. So the dimension of the kernel is 1. Now remember, the rank nullity theorem, we're going to use that again. The rank nullity theorem says that the dimension of the kernel plus the dimension of the range is equal to the dimension of V. What's V in this case? If we back up a bit, V is this guy. And we know that guy has dimension 3, right? P2R has dimension 3. So this is 3. And we just got the dimension of the kernel is 1. So this must mean that the dimension of the range is 2. So by the same reasoning as before, since the range of T is a subspace of, well, we're mapping to P2R, right? So P2R, but the dimension of the range is equal to 2, this implies that the range cannot equal the whole thing. So what this means is that T is not on 2. So T is an example of a map that is not one-to-one and not on 2. Okay, so we're now going to start talking about some interesting theoretical results here. So what is this corollary? Let's let T go from V to W, be a linear transformation, and suppose V and W are both finite dimensional. First thing, if T is one-to-one, then the dimension of V is smaller than the dimension of W. Okay, so if T is one-to-one, then the dimension of V is less than or equal to the dimension of W. Second statement. If T is on 2, then the dimension of V is greater than or equal to the dimension of W. Finally, the last one, if T is one-to-one and on 2, then the dimension of V is equal to the dimension of W. Okay. So let me try to give you guys a little bit of justification of why this is true. So I want you to think about the fact that, remember, when T maps into W, the range of T is always contained inside of W, right? In other words, this fact right here tells us that the dimension of the range of T is always less than or equal than the dimension of W. And it's equal only if it's on 2. Okay, so let's look at part 1. Oh, also, let me write down the rank nullity theorem, because the rank nullity theorem says that the dimension of the kernel plus the dimension of the range is equal to the dimension of V. So let's do all three of these above. If T is one-to-one, okay, if T is one-to-one, then that means that this guy is 0. So what does that mean? This means that the dimension, so this implies that the dimension of V is equal to the dimension of the range, which is less than or equal to the dimension of W. That's what I wrote down over here. And so that proves the first part. Now, what about if T is onto? Okay, so if T is onto, then that actually implies, so T is onto, then this means that the dimension of the range of T is equal to the dimension of W. So this implies that the dimension of the kernel plus the dimension of W is equal to the dimension of V. So something plus dim W equals dim V. So in other words, dim V is less than or equal to the dimension of W. Oh, sorry, greater than or equal to. I did that inequality wrong. Well, let me actually write it this way. Dim W is less than or equal to the dimension of V. Finally, the third one is simple. If 1 and 2 are both true, then the only way you could both be greater than or equal to something and less than or equal to something is if they are equal. Okay? So that's where part 3 comes from. Okay? So this is kind of like a mini proof of why this corollary is true. However, this gives us a nice result. Okay? So this is a theorem. Let V and W be finite dimensional vector spaces, and suppose T is a transformation that goes from V to W, and let's suppose that the dimension of V is equal to the dimension of W. Then T is 1-to-1 if and only if T is on 2. Okay. What does this mean? This means that if V and W are vector spaces that have the same dimension and T is going from V to W, then T is 1-to-1 if and only if T is on 2. In other words, if it's 1-to-1, then that means it has to also be on 2, and vice versa. If T is on 2, then it has to also be 1-to-1. This is really neat because it basically means that you get the other one for free. So, definition. If T from V to W is both 1-to-1 and on 2, then we can define another map. And we call this map T inverse. T inverse goes from W to V, and this map is given by the following. T inverse of W is equal to V if and only if T of V is equal to W. Okay, this should look familiar. This is just like when we call an inverse function, right? So we call T inverse the inverse transformation of T. Okay. So before I move on, again, what we're saying here is that if T is 1-to-1 and onto, so both those things have to be true, then we can define an inverse map. Okay? The inverse map, T inverse. Okay? So definition. Let V and W be two vector spaces with the same scalars. Okay. In other words, either they both have scalars from the reals or they both have scalars from the complex numbers. If there exists a linear transformation T which goes from V to W such that T is both 1-to-1 and onto, we call T an isomorphism. We call T an isomorphism. And we say V and W are isomorphic vector spaces. Okay. If this is true, we write it like this. Okay? So, how do we view isomorphism? Isomorphism is essentially saying that these two vector spaces are the same. Now, why don't we say that they're equal to each other? Well, they're not exactly equal because we call things differently in these two vector spaces. We don't have the same names. The vectors don't look the same. But everything in the vector space V behaves like it does in the vector space W. In other words, the only difference is the name. Okay? Same relationships, same dimensions, same everything. Okay? All right, so this is what it means to have two isomorphic vector spaces. Now, the next theorem is one of the most interesting consequences of the whole, all of linear algebra, really. So let's let V be a finite dimensional vector space such that the dimension of V is n. Then V is isomorphic to Rn. I guess I should say that this has to be a real vector space. Okay, in other words, the scalars are coming from the reals. This is extremely important. Let me put a couple of stars next to this. This is really, really, really important. What we have just said is that every n-dimensional vector space is isomorphic to Rn. So let's say this again. The consequence of this theorem. Every vector space with dimension n is isomorphic to Rn. In other words, they are also all isomorphic to each other. This is extremely important. If it sounds important, it's because it is, okay? What we're saying is that every vector space with dimension n over the real numbers is actually the same vector space as far as isomorphisms are concerned. Okay, so how would you prove this? It's actually quite simple, okay? Let's suppose that a basis for V is V1 to Vn, and we already know what a basis for W is. Basis for W, or let me not call it W, let me actually call it Rn. Basis for Rn is, let's do the standard basis, E1 to En. Okay, all you have to do is make your isomorphism map, take each of the basis elements here to a basis element over there, and this is going to be an isomorphism. You can show that easily that this is one-to-one and onto. Okay? So this definition for T, so this would be our T. T is an isomorphism. Okay, so any two vector spaces with the same dimension then are isomorphic to each other, and so we should be able to find the isomorphism pretty easily. Let's do a couple of examples, okay? So, example, determine an isomorphism T which goes from R3 to P2R. So note, they are isomorphic, right? Because the dimension of R3 is 3, and the dimension of P2R is also 3. So because they have the same dimension, we now know that they are isomorphic to each other. So let's go ahead and determine an isomorphism. How are we going to do this? Okay, well, what's a basis for R3? Of course, IJK, or we can call it E1, E2, and E3. And what's a basis for P2R? Well, the standard basis is 1x and x squared. So then we can define T as follows. I just have to tell you what to do to the basis elements. T of E1 is equal to 1. T of E2 is equal to x. And T of E3 is equal to x squared. So this is an isomorphism. This is an isomorphism. So what would T of a generic, let's say ABC be? Well, this is going to equal A plus BX plus CX squared. So this is our isomorphism, right? In other words, R3 is really the same as second degree polynomials. You can see the correspondence here. Let's try another one. determine an isomorphism, we're going to go from R4 to M2R. Now note that both of these guys, the dimension of R4 is 4. The dimension of M2R is also 4, right? These are 2 by 2 matrices. So they are the same dimension, so this is why we can say they're isomorphic to each other. Okay, so what's our map going to be? So again, our basis, let's write down a basis. A basis for R4 is E1, E2, E3, E4. What's a basis for M2R? Well, let's write down the simplest one we can think of. Sorry, I didn't mean to put that there. 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, and 0, 0, 0, 1. Okay, so I'm just going to say that T of E1 is equal to 1, 0, 0, 0. T of E2 is equal to 0, 1, 0, 0. T of E3 is equal to 0, 0, 1, 0. And T of E4 is equal to 0, 0, 0, 1. Or if you put this all together, what's T of A, B, C, D going to equal? It's going to equal the matrix A, B, C, D. Right? So we can clearly see, or let me just say that T is an isomorphism. Okay, we can clearly see then that R4 is really the same as 2 by 2 matrices when it comes to, as vector spaces, I should say. They are the same thing. Okay, thank you so much for watching this video. I'll see you next time.